Okay, we are at section 9.4, collisions in one dimension. So let's get right to the PowerPoint. There's quite a few slides here. There's about 12 or so, so we'll try to get through them. First off, what is collision? A collision is an event during which two particles come close to each other and interact by means of force. Now, if you recall back when we introduced the concept of force, we had contact forces and non-contact forces. And so we see in the top drawing here, we have a contact force where two balls of one of mass 1 and one of mass 2, they collide, and it looks like they're rebounding one from the other, one force of 2, 1, the other in the opposite direction, force of 1, 2. So the force is equal and opposite. Well, in the bottom, we have a proton approaching an alpha particle, which is a helium nucleus, and the because of the electric repulsion of like particles, uh, there's a collision. In other words, they come close together as they approach each other. They want to repel each other, and it produces a force alpha p on the uh, pink um, particle, the proton, and then a force uh, proton alpha on the beige, the alpha particle. It's a uh, helium is 2 protons and 2 neutrons. Um, so that's a collision. Both of those are collisions. Whether there's contact or non-contact, those are both collisions. Now on the atomic scale, the the, they never come into physical contact, but there is a collision nonetheless. Um, so the two particles that come together, M1 and M2, they collide. The impulsive forces may vary in time in complicated ways, but we can model these. Um, uh, we know that the momentum is always going to be conserved, but the total kinetic energy may not be, and it depends on the type of collision. Collisions are elastic or inelastic, depending on whether or not uh, kinetic energy is conserved. So, in an elastic collision, where the two particles bounce off each other, the kinetic energy uh, is is conserved. On an inelastic collision, the total kinetic energy is not the same as afterwards. Some of the energy gets used into deforming the particles. Some of it gets in, like if you can imagine two clay balls uh, hitting each other, they deform. Part of the energy goes into the deforming the balls. That's what happens in auto accidents. Part of the energy goes into crumpling the metal in the collision. That is an inelastic collision. Um, in a perfectly inelastic collision, the uh, the items stick together. In an inelastic collision, the again the kinetic energy is not the same. The momentum is the same, but they don't necessarily stick together. That's an inelastic. So we have elastic, where kinetic energy and momentum are conserved. Inelastic, where momentum is conserved, but kinetic energy is not conserved. And perfectly inelastic is where, again, total kinetic energy is not conserved, momentum is conserved, and the items stick together. So we're going to see that in the next slide of a uh, perfectly inelastic collision. Before the collisions, the particles move separately. After the collision, the particles move together. They stick. They join one another. Uh, so the uh, uh, the total momentum of the system uh, as they're approaching each other is 0. That is assuming M1 V1 is equal to minus M2 V2, so they cancel, so that the total uh, momentum is equal to 0. The after collision, the momentum initial, the change in momentum initial is going to equal the change in momentum final. So the change in momentum is going to be conserved. So uh, delta P initial equals delta P final. That means that M1 V1 plus M2 V2 equals the combined M1 M2 times V final. Now there is not a V1 final and a V2 final since they're both sticking together. There's just one V final. Okay, that's a perfectly inelastic collision. And V final can be found by, if you solve for V final in this equation, you just divide both sides by M1 plus M2, and you'll be able to find the final velocity. Let's now we're going to talk about elastic collisions, and we're gonna do a little experiment, a little demonstration using Walter Fent, our friend Walter Fent. We've gone through him several times. He's got some collision examples. Now, elastic collisions. Before the collision, the particles move separately. After the collision, the particles continue to move separately with new velocities. Now, how do we determine that? Well, we use the two equations. The initial velocity, the initial momentum equals the final momentum. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So the initial momentum has to equal the final momentum. Now, in elastic collisions, the kinetic energy is conserved. So kinetic energy initial equals kinetic energy final. So we have one half M1 V1 initial squared plus 1/2 M2 V2 initial squared equals the sum of 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Now we have two equations, and if we only have two unknowns, we can solve these and come up with the equations. But there's some quadratic terms in here, and it can be kind of cumbersome. So we're going to simplify this, and we're going to go through a procedure. Um, we take the kinetic energy equation. I'm not going to repeat it. We get rid of the 1/2 because there's a 1/2 in every term, and then we group the M1s together. You can see that we have, if we subtract M1 V1 final squared and take it to the other side, it becomes M1 times V1 initial squared minus V1 final squared. And that's equal, if we take the M2 uh, term to the other side, it becomes M2 times V2 final squared minus V2 initial squared. Okay, now, whenever you have A squared plus A squared minus B squared, you can factor that out as A minus B times A plus B. And that's what we're going to do. M1 times V1 initial minus V1 final times V1 initial plus V1 final. That's equal to M2 times V2 final minus V2 initial times V2 final plus V2 initial. Now, if we look at the momentum equation and we group the M1s and the M2s together, we'll come up with M1 times V1 initial minus V1 final equals M2 times V2 final minus V1 minus V2 initial. Now, if you look above, if we divide that middle equation by this one that we just printed, the M's cancel, and the subtractive parts of the V initial V final, they subtract also. So all you're left with is V1 initial plus V1 final equals V2 final plus V2 initial. So if we group the initials together, we'll see that V1 initial minus V2 initial equals the negative of V1 final minus V2 final. All right. Now, we're gonna simplify this and come up with different conditions. So um, this is just the conservation of momentum equation, M1 V1 M2 V2 so far, initial and final, and then that's the equation that we just got. here in the lower right-hand corner. Now, if we combine those, we see that we get this equation. V1 final is equal to the ratio of M1 minus M2 over M1 plus M2, V1 initial, plus 2M2 divided by M1 plus M2 times V2 initial. V2 final equals 2M1 M1 divided by M1 plus M2, V1 initial, plus M2 minus M1 divided by M1 plus M2, V2 initial. Well, Mr. Michaka, this is a very complicated equation. How does this help us? Well, it helps us under certain conditions. Let me catch up with my notes. And let's look at the first condition where M1 and M1 equals M2. So if M1 equals M2, you see that that first term by this first term here, M1 minus M2 is 0, and M2 minus M1 is 0. So that's going to simplify. This is when M1 equals M2. That's going to simplify. They're going to become 0. And so if they're equal, 2M over M plus M is 1. So we'll see that V1 final equals V2 initial. We're looking at the extremes. V1 final equals V2 initial. And V2 final equals V1 initial. So that simplifies it. When M1 and M2 are equal, that simplifies the equation. And you can see that there's an exchange of velocities. This is similar to when you hit a cue ball and it hits a stationary ball, the cue ball stays and the second ball takes off. So V1 final equals V2 initial. So if V2 was standing still, V1 is standing still as a final at its final position, and the opposite. V2 final equals the V1 initial. Whatever that cue ball was going at, now the V2 final, that's what its velocity is going at. Okay, now let's look at the case where special case particle 2 is initially at rest, then V2 initial is equal to 0. So if V2 initial is equal to 0, then that simplifies this equation to V1 final over the ratios times V1 initial. And let's see, I think V1 final, okay. No, that's right. Those are both right. Okay. And V2 final equals 2M1 over M1 plus M2. So in the case where M1 is much greater than M2, M1 plus M2 is approximately M1, and M1 minus M2 is approximately M1. We're talking about when M1 is much, much greater than M2. So V1 final is equal to M1, is equal to about V1 initial, and V2F is approximately twice V1 initial. And we see that at the bottom equation. V1 final is approximately V1 initial, and V2 final is approximately twice V1 initial. And we can't quite play with that with the Walter Fent because we can't make it that much larger. So this is like when an example would be a moving uranium atom strikes a hydrogen atom at rest. Okay, because the uranium is so much larger than the hydrogen. Okay, now let's look at the case where M2 is much, much greater than M1, and V2 initial is equal to 0. If that's the case, then V1 final is approximately like -1 times V1 initial, and V2 is approximately 0. V1 final equals minus V1 initial. So it's in the opposite direction, and V2 final is approximately 0. This is where M1 is much, much smaller than M2. Okay, let's take a quick quiz. In a perfectly inelastic one-dimensional collision between two moving objects, what condition alone is necessary so that the final kinetic energy of the system is 0 after the collision? The objects must have initial momenta with the same magnitude but opposite directions. The objects must have the same mass. The objects must have the same initial velocity. Well, let me tell you, if they have the same initial velocity, then they're going in the same direction. So we can count that one out. The objects must have the same initial speed with velocity vectors in opposite direction. Well, it doesn't say anything about the mass. That would be correct if the masses would be the same. The only one that really fits here is A. The objects must have initial momenta with the same magnitude but opposite directions. So M1 V1 must equal M2 V2, so that when we take M2 V2, if we have M1 V1 minus M2 V2, it equals to 0. It doesn't say anything about the masses being equal. It doesn't say anything about the velocities being equal. It just means the momenta are equal. Okay, let's we have another quiz. A table tennis ball is thrown at a stationary bowling ball. The table tennis ball makes a one-dimensional elastic collision and bounces back along the same line. Compared with the bowling ball after the collision, the table tennis ball has a larger magnitude of momentum and more kinetic energy, a smaller magnitude of momentum and more kinetic energy, a larger magnitude of momentum and less kinetic energy, a smaller magnitude of momentum and less kinetic energy. The same magnitude of momentum and the same kinetic energy. Well, the answer here is B. It's going to have a smaller magnitude of momentum and more kinetic energy. I guess I should, there we go. A smaller magnitude of momentum and and more kinetic energy. Okay, let's see, I think, problem solving, one-dimensional collisions, the conceptualize, categorize, analyze, and finalize. So if it's a perfectly inelastic collision where they stick together, you have V final equals M1 V1 initial plus M2 V2 initial divided by the M1 plus M2 because they're stuck together. And then in elastic collision, we have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And we know that V1 initial minus V2 initial equals the negative of V1 final minus V2 initial. In an inelastic collision, we know that M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And we'll use that. I'll do some example problems to show that. And you finalize, you run your calculations and see if they make sense, if they're consistent with the mental and pictorial representations, and that the results are realistic. Okay, that ends our 9.4 discussion. Next time we'll discuss collisions in 2 dimensions.